In this video, we will introduce equations of planes, which is found in section 12.5 of our text. So, although a line in space is determined by a point on that line and a vector which is parallel to that line, it turns out that a plane in space is more difficult to describe. A single vector which is parallel to a plane is not enough to fully convey the direction of that plane. But it turns out that a vector perpendicular to the plane does completely specify its direction. And so a plane in space is going to be determined by a point P naught, which is in the plane, and a vector n that is orthogonal to the plane. And this orthogonal vector n is also called the normal vector to the plane. So, in order to find the equation of a plane, we need a point P naught, which is in the plane, and a vector n that is orthogonal to the plane. So here is a picture of a plane in blue, and you see the point P naught, which is a point in our plane, and the vector n, which is perpendicular to the plane. Now, if we let P be another arbitrary point in the plane, and let R naught and R be the position vectors of the points P naught and P. So R naught is the vector that starts at the origin and ends at the point P naught. R is the vector which starts at the origin and ends at the point P. Okay, so then the vector R minus R naught is represented by the vector P naught P, the vector that starts at P naught and ends at P. And this vector can be justified using our triangle law for subtracting vectors. Now, recall that the normal vector n is orthogonal to every vector in our given plane. And so in particular, n is going to be orthogonal to the vector r minus r naught. And so since n is orthogonal to r minus r naught, that means that the dot product of these two vectors must be 0. And that's the key to finding the equation of our plane. It's the fact that orthogonal vectors have a dot product equal to 0. So, to obtain a scalar equation of the plane, we're going to suppose that the vector n has components a, b, and c. We know that r, because it's the vector that starts at the origin and ends at the point P, we know that r has components x, y, z. And similarly, we know that r naught has components x naught, y naught, z naught. So, if the dot product of n with r minus r naught is 0, that would tell us that the dot product of the vectors a, b, c with the vector x minus x naught, y minus y naught, z minus z naught must be 0. So, following our dot product, this tells us that a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And this is what we call the scalar equation of the plane through the point P naught with normal vector n equal to ABC. So this is our main equation of a plane. And notice we used our point x naught, y naught, z naught and our normal vector ABC. And because it comes from orthogonality, that dot product equals 0. So we have our equation equals 0. And that's where this equation of a plane comes from. Let's do a quick example. Suppose we want to find an equation of the plane through the point 4, 0, negative 3 with normal vector 3, 1, 2. Let's then find the intercepts and sketch the plane. All right, so we know that our normal vector is 3, 1, 2 and that we have a point in the plane given by 4, 0, negative 3. So let's write down our basic equation of a plane. We're going to replace x naught, y naught, z naught with our point 4, 0, 3 and replace our normal vector ABC with the vector 3, 1, 2. So our equation of the plane becomes 3 times x minus 4 plus y minus 0 plus 2 times z plus 3 equals 0. Now we can leave it like this, but it's probably a little more appealing to the eye to clean it up a little bit. So distributing, we have 3x minus 12 plus y plus 2z plus 6 equals 0. Or rearranging, we get 3x plus y plus 2z equals 6. And this is probably what we would submit as our equation of the plane. The equation 3x plus y plus 2z equals 6. Before we move on to intercepts and sketching, I want to point something out. Remember that the normal vector for this plane was the vector 3, 1, 2. And we see those numbers 3, 1, 2 as the coefficients of our variables x, y, z. And it turns out this always happens. If we're given a plane, ax plus by plus cz equals d, as long as a, b, and c aren't all 0, then we can read off the normal vector as the coefficients of the variables x, y, and z, a, b, c. This is a really nice fact to keep in mind. So if we're given a generic equation of a plane, ax plus by plus cz equals d, we automatically know the normal vector for that plane is the vector abc, those coefficients of x, y, z. Okay, now to the intercepts. So here's our equation of the plane, and we were asked to find the intercepts. Now the x-intercept will occur when y and z are both 0. So if we let y and z equal 0 in our equation of the plane, we're left with 3x equals 6. So our x-intercept occurs when x is 2. What about the y-intercept? Well, our plane will intersect the y-axis when x and z are both 0. And so our y-intercept occurs when y equals 6. Finally, our z-intercept. So the plane will intersect the z-axis when x and y are both 0. And so our equation then becomes 2z equals 6, so z equals 3. Therefore, the intercepts of this plane are the points 2, 0, 0, 0, 6, 0, and 0, 0, 3. And so to sketch our plane, we start by plotting those 3 intercepts that we just found and connect them together. And this doesn't give us the entire plane, but this gives us the portion of the plane that exists in the first octant. And normally when we're sketching, that's a good place to start. If you want to see a picture of the entire plane, something like GeoGebra can come in to help, which is what I use to create this sketch that we see here. All right, so that's all for our introduction to the equation of a plane. We'll talk much more about this and see a lot more examples of planes in class. I look forward to seeing you there. Bye, guys.